Hello, everybody. This is for the course MATH1251 at University of New South Wales. This is the for calculus section, and we are going to go through the problem 68. Now, we have two real numbers, positive real numbers, such that A is bigger than B. And the arithmetic mean is defined as just a mean, a plus b over 2, and the geometric mean is defined as a square root of a times b. We have two recursively defined series. So each series element defined recursively, like an plus 1 is an plus bn, and bn plus 1 is a square root of an and bn. So these are the definitions of the series. And first thing we would like to show that this inequality holds. And both series which we are going to construct are convergent. And we would like to show that the limit exists and the limits are the same for these two series. And then we were going to show what is happening with the series in terms of finding the arithmetic-geometric mean for this particular number, 648 and 8 in the end. It's like an applications of the theory and to see what's going on. Okay, so what we have, this is a series, and it's the indexed by the n, right? Indexed by n. So indexed by n, and n is a natural number. So everything is one step ahead, one step ahead. If this is the situation, we would like to, in order to be able to prove something, we would like to use induction method. This is the first thing it comes to our mind as a mathematician. You have the indices indexed by the natural numbers, and the proof should go most probably with an induction. So we need to apply the induction method in order to be able to show this inequality for that is true for each n. Now, this is a known fact. For each positive real numbers, this is the fact. So this is the first, this is B1, and this is A1 with respect to the definition that we have here. And this is true for all A and B, for whatever you started with. So this is true for k is equal to 1 for an induction step. And we assume that as an induction hypothesis, it is true for a k. So that means that bk is smaller than ak. And then we would like to show that bk is smaller than a bk plus 1. Okay, for k plus 1, bk plus 1 will be the square root of ak bk. And because of, I'm using again this equation, this fact, from here to here. And this is equal to ak plus 1. So bk plus 1 is smaller than ak plus 1. Now, bk plus 1, by definition, again, roots of the ak bk. Now, this bk, I'm going to replace with the ak, but when I'm going to do that, it will be a smaller than equal to, because bk is smaller than equal to ak. So I can replace that, so that will be smaller, but this is the square of the square root, that ak. So we found bk plus 1 smaller than ak. Right? And so this is what we are doing here, right? bk plus 1, and bk. Everything will come out easily. And then the bk is smaller than, taking this one, multiplying 1 over 2 on both sides, and then adding ak plus 2 on both sides, all of them positive. Then we have, this is ak plus 1, and this is ak, so ak plus 1 is smaller than ak. So we still need to prove that bk is smaller than bk plus 1. And again, we are using this inequality, bk is smaller than ak, and bk is positive. Then multiplying this inequality by bk, I have bk squared, ak, bk, taking a square root on both sides. I have bk smaller than bk plus 1. So as a summary, I found these inequalities all the way through, right? I found bk smaller than bk plus 1. That's what we found here. And bk plus 1 is smaller than ak plus 1, which is as 1 here. And ak plus 1 is smaller than ak, which is here. Right. So we proved that this induction by using induction inequality. Second part shows that we would like to know that these series are convergent. What they are bounded, so they are converged. Why it is bounded? Because it is bounded with the A and B. With respect to this inequality, we can write it down. Start from A is equal to A1, and then bigger than A2, and in some stage we have AN plus 1, then that is bigger than BN plus 1, then it is BN, and the BN, and the other side we have B. So A and B bounds are both series. Since they are bounded series, they have a limit. Okay, now the next step is that to show that the limit is equal. This is a tricky way to do it. It works. It is because this is indexed by n. We have a series indexed by n. N goes, let's say L is equal to limit n goes to the infinity an. And define, let's say, because we know the existence of the limit from the above part, which is parts B, then we are just calling them the limit of an is L, limit of bn is m. All we want to do now is to check they are equal to each other. That's the aim of the game for this part of the question. But since if you add 1 to the infinity, it is still infinity. So with this part of with this perspective, we have limit an plus 1 when n goes to the infinity is also L. And limit n goes to the infinity bn plus 1 is also m. So this, by using this idea, we can use the general definition of this series. Then we will have when n goes to the infinity, we have L in this side and we have L in this side. And we have an equation to solve, which we can do it. Right, so we have L plus m over 2. Then this is 2L, L plus m, you're moving to L over that side. Moving to L over that side. So L is equal to m from this equation. This equation is m square root of this is L and this is m when n goes to the infinity. We still have an equation, we can solve it. And we have m squared is equal to Lm. Then we have either m is equal to 0 or m is equal to m. M cannot be is equal to 0. It means that everything is 0. You have to start with the 0, and that doesn't make sense at all. So we don't have that case. So m has to be equal to L. So simultaneously, solution of these two equations gives us that the limits has to be the same. I think I have been losing that. So there must be m here. So this is what I mean, it's bn here. It's just a printing error. Okay, so we found the limits has to be equal as well. So next thing that the question asked is to understand or do some applications with respect to some numbers, and the number is 648 and 8. So this is the iterations. This is the iteration number, and this is an plus ans, and this is bn's. For a is equal to 0, a0 is for 648, and b0 is 8. Then the arithmetic mean and the geometric mean. And then n is equal to 2, we have these two numbers. N is equal to 3, we have this number. N is equal to 4, we are approaching to limit the situation. And then n is equal to 5, we already achieved with the limit conditions with the 3 decimal places. Of course, the infinity in this case is infinite, but the requirement was 3 decimal places, so you reach the equivalence of the 3 decimal places in the iteration of number 5. So this is all about this question. Thank you very much for listening. All the best. See you.